Hello, section 10.3, Electronegativity and Polarity. After this video, go and watch video problem 53 for a little more polarity practice. So let's talk about this idea of electronegativity. Alright, two different nonmetals, when they're bonded, they do not share the electron equally, and that's because of a difference in electronegativity. Electronegativity is the ability to attract shared electrons in a chemical bond. So let's look at a couple of atoms. Okay, let's look at, here's a small atom, so there's the nucleus. Here's a small atom. Okay, and let's say that that small atom is going to bond with this larger atom. So here's a larger atom. Now think back to Coulomb's law. Coulomb's law, which is force is equal to K, Q1, Q2 over R squared. Where as this distance gets smaller, this force gets bigger. So let me put a couple of electrons on here. Here's one electron. Here's the other electron. Alright, and now let's show that force of attraction. So here's the small atom, and there's the distance to the electron of the other atom. Here's this large atom, and there's the distance. So obviously, we'll call this R1, we'll call this R2. R1 is smaller than R2. That smaller atom is closer to the other atom's nucleus. Let's give these a couple of names here. Let's say that this is atom A. This is atom B. So atom A is smaller. Its nucleus is closer to the other atom's electron. Since it's so much closer, there's a greater force of attraction. And that's the electronegativity, the ability to attract shared electrons in a chemical bond. And you'll see that this difference in electronegativity, this difference in the attraction for the other atom's electron, really determines whether it's covalent or ionic. But within covalent, it determines whether it's polar or nonpolar. Right? So let's take a look. A little more about electronegativity. Fluorine is the most electronegative. Cesium is the least electronegative, and you can see why. Why is fluorine the most electronegative? It has the smallest atomic size with a strong positive nucleus. Why is cesium the least electronegative? Large atom, relatively weak nucleus. So again, if we go back to our pictures, here's fluorine, here's this small atom fluorine, here's this big atom cesium. Right? The distance from this nucleus to the other atom's electron is large, where this distance from this nucleus to the other atom's electron is small. So all of these electronegativity values here, these are all Pauling scale values, named after Linus Pauling, who just died recently, not too long ago actually. So you can see it's on a scale 4.0 being the largest for electronegativity. And this scale, you don't have to memorize this. You rarely use this. More often you have to look at, you have to make predictions of the difference in electronegativity based on where they're at in the periodic table. Okay? So further to the right and further up is highly electronegative. Further to the left, further down is not very electronegative. Polar and nonpolar. Let's just talk real quick what polar and nonpolar means, because we're going to get into this idea of being nonpolar. So here's this molecule. All right, here's just the generic molecule. If it's neutral, in other words, it's nonpolar, that means that its electrons are distributed equally. There is no positive and negative end. Where a polar molecule now, we're going to have, let's say, more electrons on this side. So here's more electrons, fewer electrons on the other side. So on the electron heavy side, it's going to have a negative charge. On the non-electron heavy side, it's going to have a positive charge. But the entire molecule is neutral, right? A positive one and a negative one are going to cancel each other out. So the entire molecule is still neutral. It's just that the electrons aren't shared equally. They're more on one side than they are on the other. Okay, and that's a polar molecule. Where again, a nonpolar molecule, those electrons are now distributed equally. Right? So as far as difference in electronegativity, what do we have? Well, if it has a very, very small difference in electronegativity, anywhere from 0 to 0.4, then it's considered a nonpolar covalent bond. So these are often element with itself, so like a chlorine-chlorine bond, that's nonpolar because that chlorine has electronegativity value of 3. This chlorine has electronegativity value of 3. If we take the difference between the two, so if we subtract them, we will get 0. All right? Now another common one is the carbon-hydrogen single bond. So a carbon-hydrogen single bond is nonpolar, and the reason why is because carbon has electronegativity of 2.5, hydrogen electronegativity 2.1, so the difference between these two is 0.4, which is right at the cusp of being polar and nonpolar. So I had to take a drink. Now, when it's nonpolar, okay, when we have the small difference in electronegativity, the electrons are shared equally. Why is it always doing that? Right, so nonpolar, the electrons are shared equally. And we can also say that usually when it's nonpolar, we're talking about two atoms of similar size. Okay, because in nonpolar, if I go back to the idea of my atom here, here's one atom, here's the other atom, both about the same size, you'll see that there's no difference or very little difference in the force of attraction. Right? That distance really isn't that big of a difference, and so they pull on those opposite atoms' electrons with about the same amount of force. Now a polar covalent bond, now we're talking about a difference of 0.4 to 1.8. And again, you usually don't use the scale. Anytime that you need to use the scale, typically you'll be given those electronegativity values. Once we get here, we're talking about an unequal sharing of electrons. All right. So now we're talking about basically two different atoms. So let's say like a chlorine-fluorine bond. So here's chlorine, here's fluorine. Fluorine has an electronegativity value of 4, most electronegative. Chlorine is 3.0, which gives us a difference of 1, which means that it's, you know, between 0.4 and 1.8. So that's going to be polar. Polar basically tells us that the electrons are on one side more so than the other. So if I'm looking at here's a molecule, here's, let's say, one nucleus, here's the other atom's nucleus, right? So if atom B is more electronegative, what will happen is if we look at what's called an electron cloud density, or the electron density, we'll see that the electrons are around the B atom more so than the A atom. So here is the electron cloud where the electrons can be found most of the time. Notice that around B it's much larger, around A not quite as large. So what we end up with is we end up with a negative charge over here because the electrons are there more often, and a positive charge over here because the electrons aren't there as often. Now to signify that, we usually use a lowercase delta, which means a partial charge. Okay? So that's a lowercase delta. We know what a capital delta is. That's a capital delta. All right. Now, an ionic bond is now when we have a difference greater than 1.8. So if we look at these atoms, now we're going to see a large difference in size of the atom, right? So here's going to be that's going to be the nonmetal, because it's pretty small. Here's going to be the metal, which is pretty big, right? So this nonmetal, let me move that over a little bit here. Scoot this, scooch a little bit closer, scoochy, scoochy. There we go. Give it some electrons, electron there, electron there. So look at this. There's very small distance between the protons and the other atom's nucleus, or the other atom's electrons. Here, much larger distance. And so this force of attraction right here for this nonmetal is huge. And it's so huge that it doesn't just attract the electron, it completely steals the electron. And so it creates an ionic bond. So you can think of an ionic bond as an extreme polar. because now instead of sharing, it has completely taken that electron away. So if we're talking about atom size, ionic bond is a big atom and a small atom typically. A polar covalent bond is again a big atom, small atom, but not a huge difference. And you can see, according to the electron, usually for ionic bond we say, hey, it's a metal that's been bonded with a nonmetal. That's what we typically say for an ionic bond. But you can see even some of these aren't going to give us an ionic bond. Or yeah, so take a look at something like magnesium, which has an electronegativity of 1.2. If magnesium were to get with iodine, iodine has an electronegativity of 2.5. You can see there, that's actually just a polar bond. It's really polar. Magnesium iodide would be really polar. But according to electronegativity difference, it's just a polar bond. And so what we have is this table 10.4. We have this gradient, all right, where it goes from nonpolar to polar, then over to ionic, and you can see there is no hard, fast line. It's not like 0.4 is something special. It's just that that's what we've decided is nonpolar. So you can see here in this nonpolar, the purple represents the electron density. Okay, the electrons are distributed equally. Here in this polar bond, the electrons are not distributed equally. The electrons are more around this atom, okay, which is why it has a partial negative charge, so that there's that lowercase delta. So we can also assume that this is the atom with the most electronegativity between these two. And then here's an ionic bond with just a transfer of electrons because of a huge difference in electronegativity. Now, that leads us to looking at what is a polar covalent bond. So nonpolar, again, let me just refresh your memory. Nonpolar, we're talking about like a chlorine-chlorine bond or a nitrogen-nitrogen bond. So those are nonpolar, or a carbon single bond hydrogen. Those are all nonpolar. If we're talking about polar, what we mean is that the electrons are shared unequally. Okay? They're found more often around the more electronegative atom, and this creates what's termed a dipole. Now, it's also referred to as a dipole moment. So there's another term that means that is analogous to polar. So in this case, we have a positive end and a negative end to the particle. The bigger the difference in electronegativity, the more polar it is, and that's important to be able to recognize, right? You can't just be polar or nonpolar. You can be really, really polar, just kind of polar. Now, here are some ways that we show polarity. Here's a carbon-oxygen single bond. Right? In this carbon-oxygen single bond, this should just be a single line. In this carbon-oxygen single bond, oxygen is more electronegative. Carbon is the less electronegative in this case. And so what happens is that my G and my E. What happens is that this oxygen attracts the electrons with a greater force. If we're talking about atom size, right, the oxygen is smaller than the carbon. We know that from our periodic trends, atomic radius. Again, that'll come back again and again. Pretty important idea. So the oxygen is going to attract the electrons more so than the carbon. It's more electronegative. It's smaller, has a greater force of attraction for the other atom's electrons. And so what happens is the electrons spend more time around that oxygen than they do around the carbon. So that means that the oxygen has a partial negative charge, while the carbon has a partial positive charge. Now, another way that we can show that is right there with that arrow. So the arrow is pointing toward the more electronegative element, and then we put a plus on the end of it on the side of the less electronegative element. Sometimes these can also be drawn right on the bond, like that. Okay, so there's just a couple ways that we can show a polar bond. Now, just because it has polar bonds, just because a molecule has polar bonds, doesn't mean the molecule itself is polar. A molecule can have polar bonds and still be nonpolar. Let's take a look at some examples here. What we're going to be looking at is we're going to be looking at the bonds in the molecule, but also the shape. And that's what determines whether it's polar or nonpolar. So the reason that something is nonpolar, let's jot this down here. The reason that something is nonpolar is there could be a couple reasons. One, only nonpolar bonds. And then two, the electrons are shared equally. And three, the let's save three. We'll save three. Okay, so if we're talking about A here, nonpolar bonds that make nonpolar molecules. Why are they nonpolar? Well, this is a nonpolar bond. No difference in electronegativity. No difference in electronegativity. This small difference in electronegativity, but it's still nonpolar. Okay, so in other words, all those bonds are nonpolar. Nothing is pulling the electrons more so than the other. Okay. Now, let's talk about polar bonds that cancel out. Now we're going to introduce this third idea. So now we're going to introduce this number 3. Now, we said only nonpolar bonds, it's going to be nonpolar. If the electrons are shared equally, we said it's going to be nonpolar. Those are the reasons. Number 3, the third reason of why something can be nonpolar but made of polar bonds, and let me write that down, nonpolar but made of polar bonds. Move my 3 down a little bit. Now, this is going to be because there is no net movement of electrons because the shape allows for the force of attraction to cancel out. Okay, so don't do this to your notes here, but what if I had just C double bond O? Alright, if I had just C double bond O, that would be a polar molecule, right? C double bond O. But I don't have just C double bond O. I have C double bond O on both sides. So this oxygen is pulling with a certain amount of force, right? So here's this force of this oxygen. Well, guess what? This oxygen is pulling with the same amount of force. Since this is a linear molecule, the dipoles cancel out. There is no net movement of the electrons. So imagine that here's the carbon, right? And imagine we are pulling on the rope. So here is, everybody likes John Cena now. So here is John Cena on this side pulling on the rope. Here is John Cena on this side pulling on the rope. Will the rope move? John Cena cannot be John Cena. The rope will not move, right, if we're playing tug of war. So that means that these electrons won't move. No net movement of the electrons. Why? Because the shape says so. Okay, let's look at another example. Here's a tetrahedral molecule. It's CCl4. So a CCl bond, so just one of these bonds is polar, right? But since they are all 109 degrees, which is as far away from each other as you can get without getting closer. So since they're all 109 degrees, they all cancel each other out because they're all pulling with the same amount of force. So that makes it nonpolar. What happens if the shape isn't such that they'll cancel out? So what happens if we have polar bonds that do not cancel out? So here's water. Right? Water is, there's a hydrogen on one end, hydrogen on the other end. Oxygen is the more electronegative here in this case. Okay? Now take a look at this. It's almost like a force vector diagram. Right? So we're pushing this way, right? We're pushing this way. Is there anything to balance out those pushes, those forces? No. There's nothing to balance it out. So that means we will have a net movement, which now makes it polar. So let's jot that down. 4. If the forces are not balanced, we will have a net force on the electrons and an unequal sharing of electrons. Therefore, 3 little dots in a diamond, therefore a polar bond, or a dipole moment, or a dipole. Okay? Let's look at another one. So that's water. Here's NH3, which is ammonia. Right? The nitrogen-hydrogen bond is definitely a polar bond. And again, if we look at this sorted force diagram down here, we can see that these 3 force vectors are not balanced out. So that means we have net movement of the electrons, which means that we have a polar bond. And now here's the last example, and that's CH3F. So we know that this carbon-hydrogen bond is nonpolar, 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 right? But this CF bond is polar. So now we only have one force pointed away from that carbon, and it is not balanced out. Therefore, we have a net movement of electrons. Now, very important, what I just went over, those are the reasons why a polar bond is formed. Okay? That's the reason why. Now I'm going to show you a trick to determine whether it's polar or nonpolar, but very important, the trick is not the reason why. Okay? So here you go. So what you can do by looking at the Lewis structure. Okay, look at the Lewis structure. If it is surrounded by different atoms, or if it has lone pair electrons on the central atom, it's polar. Now that's not 100% of the time. It is here, but in AP we'll change it because there are a couple exceptions. I'll tell you what those exceptions are. I'll go ahead and tell you. If the molecule ends up being linear, but it has lone pair electrons on it, then it is nonpolar. Or if the molecule ends up being what's called square planar. And again, we won't get into this year, but in AP we will. Okay? So those are the only exceptions to the molecule being polar. So these guys are actually nonpolar. Those are the exceptions. We'll talk about it in AP. Now, nonpolar, it has to be surrounded by the same atom with no lone pairs on the central atom. Boom, that's it. So if you look at the Lewis structure, and if it has lone pairs on the central atom, it's polar. If you look at the Lewis structure and it's surrounded by different atoms, it's polar. If none of those two, if either of those two is not true, it's going to be nonpolar. Okay? Being able to predict quickly whether it's polar or nonpolar by looking at the Lewis structure, very important. So make sure that you do the mastering on this and work on and take a look at those video problems. If you need more help, just ask.